Hey, so today is a continuation from day one kinematics. So one key idea we want to remember from last day is that if we have two vectors that are in the same direction, we can just add them up very easily. As a reminder, so for example, if we had a vector like so, two in the same direction, like 2 and 2, this results in a single vector and we add them together of length 4. However, if we had two vectors like this, 2 and 2, we cannot simply just say 2 and 2 is 4 because the vector, in this case, is talking about displacement. We're wondering what the length of this line is. So one of the key ideas we want to remember is that any vector in two-dimensional space, this also extends to three-dimensional space when you move on to future topics that we'll cover, as well as in university if you choose to go at the physics route. If I have some vector v, like so, instead of thinking of it as a vector that goes up and to the right, we can think of it as having an x component, and call this vx, as well as a y component, and call that vy. Okay. So our horizontal x component and our vertical y component, that when combined together, results in our overall vector v. Also, we want to make sure we remember how trigonometry works. Here's a little quick trig review. So we don't remember a triangle. Here it is. There's a right angle triangle. A, B, and C with some angle theta. Remember SOHCAHTOA. Toa. This tells us that sine theta is equal to opposite over hypotenuse, so B over C. We have cos theta, that's equal to adjacent over hypotenuse, so in this case A over C. And we have tan theta, opposite over adjacent, which is in this case B over A. Also, don't forget about the Pythagorean theorem. A squared is equal to A squared plus B squared is equal to C squared. And lastly, lots of times, I'll be skipping a mathematical step. I won't always start with this sine theta is equal to B over C. Often I'll be like, okay, this B is equal to C sine theta, or this A is equal to C cos theta, and so on. B is equal to A tan theta.